Hi everyone, this is Kaushik, working as Assistant Professor in EC Department from MLR Institute of Technology. Welcome back to the session. In this session, we're going to discuss about BCD addition and subtraction. And firstly, we're going to discuss about what is BCD code. And after that, we're going to discuss about advantages and applications of the BCD code. Thereafterwards, we're going to discuss about how to perform the addition of two BCD codes and what are the rules and how to compensate the result. And after that, we're going to discuss about BCD code subtraction and its rules. Okay, first let's look into the what is BCD code. Now let's look into this actually. What is full form of BCD? Full form of BCD or acronym for the BCD is binary coded decimal. Binary coded decimal, which means in this the decimal number, in this each digit of a decimal number is represented with its 4-bit binary equivalent. 4-bit binary equivalent. Okay, that means whatever the BCD number, for example, if you consider 123, this is a decimal number. You are supposed to represent with its equivalent BCD code. That means each digit of this decimal value, each digit of this decimal number should be represented with its 4-bit binary equivalent. 4-bit binary equivalent. That means 4-bit binary equivalent for this 3 is 0011, and for 2 is 0010, and for 1 it is 0001. Together, this entire binary code is considered to be your BCD code. Okay, now in this BCD code, the unique numbers, the unique valid numbers, the valid codes are present between 0 to 9. 0 to 9 are considered to be your valid codes, and the invalid codes are whatever the numbers other than 0 to 9 to be considered as invalid codes. Okay. To correct the invalid codes into the valid codes, you are always supposed to add 6. If you're performing addition, you're supposed to add 6. For performing subtraction, you're supposed to subtract -6. That is, 6 means you're supposed to represent again its 4-bit binary equivalent, which means 6 means 0110. And in case of subtraction, you're supposed to do it 0110. Okay. Now, what is the other name for the BCD code? It is also called as 8421 code or 8421 BCD code. Okay, why we are calling this one as 8421 BCD code? Okay, now if you look at this, this is some kind of positional weightage, related to our binary. Okay, because we are representing each and every digit of the decimal value as its 4-bit binary. If you consider this 3 itself, 0011, right? What is the positional value for this one? What is the positional weightage? As we are representing in terms of binary, the positional weightage is 2/0 in generally. This positional weightage is 2/1, and this positional weightage will be 2 square, and this positional weightage will be 2 cube. And the value for this 2 cube is 8, 2 square is 4, and the value for 2/1 2, and the value for 2/0 it is 1. Here you can observe why we are calling this specific BCD code as 8421 code or 8421 BCD code. Depending on its positional weightage, it named as 8421 code also. Okay, and that's why this is comes under weighted codes. Weighted codes. Okay. Now let's look into its applications. Advantages as well as applications. Now, first advantage, if you look into this, easy to convert. That means we can able to convert each and every decimal value from its decimal to binary or binary to decimal. It is very easy to convert. Human readable. Yeah, it is human readable because all we are supposed to remember is from the digits of 0 to 9. That means we can able to easily understand understand the values, as well as it is very easy to debug the code as well. Okay, now let's look at the third one, error detection. As right now I said that only we are having invalid codes as from 0 to 9. Whatever the value beyond this range considered to be invalid codes. That means we can able to easily detect the errors in the given code. And no conversion of errors. No conversions of error means we don't need to do any kind of additional conversion, right? Simply we need to represent the each and every digit of a decimal value in terms of its 4-bit binary equivalent. That means possibility of conversions errors will be very less. Okay, these are our advantages of our BCD code. Now let's look into the application. When you come into the application, majorly we need to focus on two things, right? One is representation of data, like numerical data representation. Okay, the second one will be data conversion. Depending on these, the BCD code will be applied or applicable into several major applications, and some of them I have represented here. For example, calculator and digital clocks. Here most often we are utilizing for data representation, as well as if you look into this one, scientific instruments. Here also majorly we are utilizing for numerical data representation only. Okay, we don't need to convert any data. All we need to do is display the numerical data here. Okay, now if you observe computer systems as well as some kind of programming language, in that case you need to perform some data conversion, like decimal to some kind of hexadecimal conversion or decimal to binary conversion that we need to perform. So in that case we are utilizing data conversion approach. And here if you look into the digital signal processing and control system as well as embedded system, maybe in the microcontrollers, in that case also still we are utilizing data conversion purpose only. Got it? Now let's look into the how we are performing BCD addition and what are the possible rules that we are supposed to learn while performing BCD addition. For example, let's say that initially first we need to represent all given decimal value, all decimal digits with its 4-bit binary equivalent, with its 4-bit binary equivalent. After representing its 4-bit binary equivalent, let's say that for example it is 1, 2, 3 and 4, 5, 6. For example, here I am representing here and as 1, right? That means 0, 0, 1, and 2 means 0, 0, 1, 0, and 3 means 0, 0, 1, 1. 4 means for this one 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. If I am performing some kind of addition for these two numbers, in that case you need to majorly focus on individual groups first, individual 4-bit binary groups first. If there is any kind of carry is generating from one group to the next group, if after performing addition we might get some result, after performing addition, if this result is generating any kind of carry to the next group, in that case you are supposed to add 0,110 to correct your resultant sum value. In order to correct your resultant sum value, you are supposed to add 0,110. Not only that, if this resultant sum is generating some kind of invalid codes, okay, whether it is generating invalid codes or if it is carrying some kind of extra carry to the next group, in these two cases you are supposed to add 0,110 to the respective group only. Okay, not to the carrying one. Whichever is responsible for generating the carry for that group, you are supposed to add 0,110. As well as if it is generating invalid codes, in that case also you are supposed to add 0,110. If it is not an invalid code or if it is not carrying any extra carry bit to the next group, in that case we don't need to perform any kind of the correction to the resultant sum value. Okay, now let's jump into the let's consider one problem. Okay, here perform the BCD addition for the following numbers 679.6 and 536.8. Let's try to represent those values. Okay, 679.6. For this, the BCD value will be, we are supposed to represent each and every digit with its 4-bit binary equivalent. In that case, 6 will be 0, 110, 7 will be 0, 1, 1, 1. That is 4-bit binary equivalent of 7, and the 9 will be 1001. Decimal point. After that, 6 will be 0110. Right. Next, after that, 536.8. 5 will be 0101. 3 will be 0011. And 6 will be 0110. After that, 8 will be 1000. These are the 4-bit binary equivalent for the given BCD, given decimal values. So now we are supposed to perform the addition. It's like a regular binary addition. First step will be regular binary addition. Go for that. 0 plus 0, it will be 0. 1 plus 0, it will be 1. 1 plus 0, it will be 1. 0 plus 1, 1. Now let's look into this. 1110. 1110 is beyond the range of 0 to 9. Beyond the range of 0 to 9. That means 1110 is a invalid code, and it is 14, right? It is 14. In generally, what is the binary equivalent for the 14? It will looks like 1 0 1 0 0. This is the binary equivalent, which is not represented in terms of 4-bit binary, right? Which is not represented in terms of 4-bit binary. If you look into that, this is clearly 5 bits, right? In generally, for example, if it is 14. In generally, when we are doing performing BCD, each and every digit should be represented with its 4-bit binary equivalent. Now, if you represent this one also 0001, 4 will be 0100. The value will be almost similar. The value will be almost similar. Got it? If you, for example, let's say that it is invalid code. To correct the result, we are supposed to add 0110, that is our 6, right? So in that case, let's add this value 0110. Now what's the value? 0011 extra carry 0, 111, it is 1. Now 101, it is 1, it is 0, 10100, and that's why we are adding extra digits, so that to correct the value, correct the actual invalid code into respect to our BCD valid codes. Okay, in generally 14 will be generally 1110. If you are supposed to represent that in terms of the binary, coded decimal, the value will be like this. And if you are trying to how we are correcting means by adding extra 0110. If you convert the value after performing addition, also still it is representing the same kind of value. So that's why we are adding, for whatever the invalid codes, we are adding additional 6. Okay, in case of the subtraction also, we are doing the same kind of operation. If you perform 0110, the code will be converted into the valid code. Okay, now let's start to perform the rest of the addition. 101 101 again 101 again 110 again 1, and again this one is also an invalid code because it is not present between the 0 to 9. It might be having extra digits like this. It's not a single digit, right? So it is extra digit. Now let's focus on the rest of the addition. 1 carrying 1, and the resultant sum will be 0. 111, that means it is 11 10 11 10. And again it is also out of the range 1010, that is the 10. It is carrying the 2 digits. Okay, 01 1 10 1 11 1. Now whatever the resultant sum which is generated by individual groups addition, all are generating invalid codes only. All are invalid codes. Of course, they are not generating any kind of the carry, but they are generating invalid codes. In that case also, you are supposed to add 0110 to the respective sum. That means for all these group values, you are supposed to add 0110. Okay, these all are invalid codes. To correct the result, we need to add 0110. Just now I have shown how we are doing that. Right, now let's do that. 0 0 0 1 1 1 0 111, it is 1 1 1 1 again. We are carrying here. In this case, we don't need to, as people might be thinking that right now we are carrying some value, right? We are correcting the result. In that case, even if you are carrying the value also, even if it is generating some kind of carry also, you don't need to add additional 6 again. Okay, Now let's perform the rest of the addition. 1 1 1 0 triple 1 1 1 triple 1 1 1 1 1 1 0 0 0 1, because we are having the carry here. 1 1 1 0 1 1 1 0 1 1 1 0 1 1 again 1 0 triple 1, it is 1 1 1 1 1 0 1 1 1 0. Additional carry, just write it and add extra additional 3 digits. Nothing, it doesn't make any difference. Now let's try to represent each and every binary value with respect to its BCD value. Right? 0 0 1, it is 1, it is 2, and it is 1, and it is 6, and it is 4. That means my resultant value is 1216.4. Now let's check out 679.6, 536.8. Let's perform the addition. 8 6, it is 14. 9 plus 1 10. That means it is 6. That is 6. 7 plus 3 10, and again it is 1. 7 plus 3 10, again it is 6. Sorry. 9 plus 6, 9 plus 1 10, 16. 9 plus 1 plus 3 10, it is 11. 6 plus 5, it is 11, and again it plus 1, it is 12. 16.4. It is matching with respect to the BCD addition. Okay. Now let's look into the subtraction rules and how to correct the subtraction. Okay, BCD subtraction. It is also like a regular binary subtraction only. First, we need to represent each and every digit with its 4-bit binary equivalent. 4-bit binary equivalent. There onwards, you are supposed to perform the subtraction with respect to individual groups. Here, subtraction results either the difference, or we are supposed to borrow from the some other digit. That means, as we are representing 4-bit binary, that means we are all considering them as a individual groups, right? For example, if one group is generating some kind of value which might be some kind of invalid code, or it might be taking some kind of borrow from the its next group. In either cases, you need to subtract the resultant value from 0.110. That means whatever the value which is generated, it should be subtracted with respect to the 0.110. In two cases, what are those? If we are taking borrow from other group, or you can say next group, or if the resultant subtraction value might be generating some kind of invalid codes. In either of the cases, you need to subtract the resultant value from its 0.110. Okay, let's look into the example. With that, we can able to do it very easily, right? Now focus on this one. 206.7 and 147.8. For that, we need to perform the BCD subtraction. Right? Let's try to represent the each and every value in terms of its 4-bit binary equivalent. Okay. 206.7. What's the value? 2 0 0 1 0 and 0 4 zeros and 6 0.110 0.7 0 1 1 1. Right? Next value will be 147.8. Right? 147.8 means 1 is 0 0 0 1, the 4 is 0 1 0 0, the 7 is 0 1 1 1, and the 8 will be 1 0 0 0. Fine, 1 0 0 0. Now let's try to get the subtraction. It's like a regular binary subtraction only, right? 1 minus 0, it will be 1, right? 1 minus 0 again 1, 1 minus 0 again 1, 0 minus 1, here it is not possible. That means we are supposed to borrow some value from the next group. This is one group, right? This is one group. For this group, we need to take some borrow from the its next group. Just now I said that if you are taking borrow, in that case, whatever the resultant value, it should be subtracted with respect to 0,110, right? Let's try to get the borrow. Can we able to get the borrow from here? No, we are not in a position to do that because it is also a 0. In that case, you need to borrow from here. Okay, fine. We took the borrow here. It is 2. It is borrowed amount value will be 2 because the base value of the binary will be 2. So the borrowed amount value will be 2. From here, I am taking the borrow as 2 again. That means the remained value here it is 1. Remember this. Here it is. Remained value will be 1. Here it is 2. 2 minus 1. It is 1. Fine. Obviously, it is an invalid code. This is clearly an invalid code generated, right? After subtraction, it is generating some kind of invalid code, right? So in that case, we need to subtract from 0,110. Let's focus on the rest of the subtraction. Then we will try to do whether we are supposed to do the 0,110 subtraction or not. We will look into that, right? Now here the resultant value will be 1. 1 minus 1, it is 0. 1 minus 1, it is 0. Now here the borrowed, already we took the borrow value. That means the resultant value becomes, here it is 0. Can we able to perform the subtraction? It is not possible. Let's try to get the value from the very next bit, that is 2. Here it is 2 now. 2 minus 1 again, it is 1. 2 minus 1, again 1. Can we able to perform subtraction here? Because we already took the borrow value. That means the resultant value at this position will be, it is 0. We are not in a position to do that. That means we are supposed to take the borrow from here. It is not possible. It is not possible. It is not possible. Here also not possible. Here also not possible. Here also not possible. Here we can able to take the borrow from this. I took the borrow to this position. It will be 2. To this position, 2, 2, 2, 2, 2. From here, I'm taking the borrow, which means from 2, I'm taking 1 unit value. That means here it will be 2, and here it becomes 1. From each and every position, it is happened like that only. That means all these units are converted. All these unit values are converted into 1 only, because we are borrowing, right? We are borrowing 1 value to the next group. Initially we are having 2. After that, we are borrowing the value. That means from the 2 units, we are taking 1 unit as a borrow. That means the remaining unit will be 1 only. That means here also it becomes 1 only, right? Now let's look at this. Here it is 1. Here it is 2. 2 minus 1, 1. 1 minus 0, 1. Still it is an invalid code. Now let's look into this one. All these values are 1s, right? 1 minus 0, it is 1. 1 minus 0, it is 1. 1 minus 1, it is 0. 1 minus 0, again it is 1. It is also an invalid code. Now let's look into this one. Here the value will present. Here it is 1. 1 minus 1, it is 0. It is 0. Here it is 2. Here it is. We are already taking the borrow. The remaining value will be 1. 1 minus 1, 0. That means here the value will be remained as 0 only. 0 minus 0, 0, 0. Right? Here it might not be generating any kind of the invalid code. Right? So the rest of the values are generating invalid codes. In that case, the rest of the resultant group sum values should be subtracted with respect to the 0,110. Not for this one. Okay. Now let's do that one. 1, 1, 0. 1 minus 0, it is 1. 1 minus 1, it is 0. 1 minus 1, it is 0. 1 minus 0, it is 1. It is a valid code. Right. Now let's focus. 0 minus 0. 0. 1 minus 1, 0. 1 minus 1, 0. 1 minus 0, it is 1. 1 minus 0, 1. 1 minus 1, 0. 0 minus 1, it's not possible. Take the borrow. 2 minus 1, 1. Do we have any value here? The value is already taken as a borrow. That means the 0 value will remain. 0 minus 0, 0. And this value will be written as it is. Now let's try to write its BCD value here. 0, 5, 8.9. This is our resultant subtraction value. Let's try to get this value. 206.7 minus 147.8. 7 minus 8, it is not possible. Can we able to take the borrow? Yeah, obviously we can take the borrow. That is a 10. That is a 10. Because it is decimal, right? Here it is decimal. That means the borrowed amount value will be as equals to the decimal value as equal to the decimal base system. That is a 10. 10 plus 7, it is 17. 17 minus 8, the resultant value will be clearly 9. And here the remainder value will be 5. Because 1 unit is taken as a borrow. And the remainder value will be only 5. Now can we able to do the 5 minus 7? It is not possible. In that case, we need to take the borrow here. That means 2 minus 1 unit is taken. That means here it is 10. If you're taking the borrow again, the resultant value here it is 10. 10 plus 5. 10 plus 5 will be 10 plus 5 will be 15. 15 minus 7, the resultant value will be 8. But here the borrowed value is 10. From this 10, we are again taking the borrow. The remainder value will be 9. Right? 9 minus 4, 5. from this position, we took the borrow value as 1. That means the remaining value will be 1. 1 minus 1, it is 0. 58.9. Right? And this way we are supposed to perform the BCD subtraction. Okay. In our next session, we're going to learn about how to perform BCD subtraction with respect to the R's complement as well as R minus 1's complement. Okay. As well as we're going to discuss about excess 3 code and its excess 3 addition as well as excess 3 subtraction.